CPU architecture overview. Imagine a symphony orchestra where each musician plays a distinct role, yet all must work harmoniously to create music. The CPU or central processing unit is much the same. It's the brain of every computer, orchestrating data and instructions to bring your software, games, and apps to life. But how does it do this? Let's dive into the fascinating world of CPU architecture and unravel its inner workings. At its core, CPU architecture is all about design. How the CPU's various components work together to process instructions and data efficiently. Think of it as the blueprint of the processor. It not only defines the components but also dictates their interactions, ensuring seamless execution of tasks. The CPU executes millions, if not billions, of instructions per second. This requires a meticulously designed architecture comprising components such as the control unit, arithmetic logic unit, registers, cache memory, and more. Let's start by breaking down these key components. First one, the control unit, the conductor. The control unit is like the conductor of an orchestra. It does not perform computations, but ensures that everything happens in harmony. The control unit fetches instructions from memory, decodes them, and sends the necessary signals to other components to carry them out. In short, it manages the flow of data and operations. Second one, arithmetic logic unit, the problem solver. The ALU is the CPU's math and logic expert. Whether it's simple arithmetic like addition or logical comparisons like is A greater than B, the ALU handles it all. Need to compute 2 plus 2 or check if a condition is true, that's the ALU in action. Third one, registers, the quick access memory. Registers are the CPU's scratch pad, tiny, lightning fast storage locations that hold data temporarily. They are like sticky notes you jot quick ideas on during a meeting. From general purpose registers for calculations to special purpose ones like the program counter and stack pointer, they are indispensable for rapid data handling. Fourth one, cache memory, the secret weapon. Ever wondered why modern CPUs are so fast? Cache memory is one of the reasons. It's a high-speed storage layer closer to the CPU, reducing the time needed to fetch frequently used instructions and data. Levels of cache L1, L2 and L3 balance speed and capacity to keep things running smoothly. Moving to the fifth one, the bus system, highways of communication. The bus system is the CPU's road network, transporting data, addresses and control signals between the CPU, memory and peripherals. Think of it as a bustling city where data travels on data buses, addresses on address bus, and commands on control buses. Now, on to the types of CPU architectures. Now that we know the key players, let's explore some architectural styles. First one, von Neumann versus Harvard architecture. In the von Neumann architecture, instructions and data share the same memory, much like sharing a single lane on a highway. Simple, but it can cause traffic jams, a phenomenon called the von Neumann bottleneck. Harvard architecture, on the other hand, uses separate lanes for instructions and data, allowing for parallel processing and faster performance. Second one, CISC versus RISC. CISC or complex instruction set computing is like a Swiss army knife, offering a vast array of tools in one place. Meanwhile, RISC or reduced instruction set computing simplifies things with fewer instructions, focusing on speed and efficiency. Most modern CPUs blend these approaches for optimal performance. Third one, multicore architecture, the power of teamwork. Why settle for one brain when you have multiple? Multicore CPUs integrate several processing cores on a single chip, enabling multitasking and parallelism. It's like having a team tackle tasks together rather than relying on one individual. Now we can check what are the advanced features in modern CPUs. The most important one, pipelining, assembly line efficiency. Pipelining is like an assembly line where multiple instructions are processed simultaneously at different stages. While one instruction is being fetched, another is decoded and yet another is executed. This overlap enhances the CPU's throughput. Second one, hyperthreading, thinking in parallel. Hyperthreading allows a single core to handle multiple threads, making it appear as though there are more cores than physically present. It's a clever trick to maximize resource utilization. Third one, integrated GPUs. Some CPUs come with integrated GPUs, making them capable of handling graphical tasks without a dedicated graphics card. This is particularly useful for compact devices like laptops and smartphones. Now, moving on to the trends and the future of CPUs. The evolution of CPU design never stops. Here's a glimpse into the future. Shrinking transistor sizes. With each generation, transistors get smaller, boosting performance and reducing power consumption. Think of Moore's law at work here. Heterogeneous computing. Mixing general purpose cores with specialized ones for tasks like AI and graphics is becoming common, as seen in ARM's big dot little architecture. Quantum and neuromorphic computing. On the horizon are CPUs inspired by the human brain or leveraging quantum mechanics for unparalleled processing power. From your smartphone to the world's fastest supercomputers, CPUs power them all. Their architecture, an intricate dance of logic, arithmetic, and data flow, is a marvel of engineering. As we innovate further, the CPU will continue to redefine what's possible in technology. And remember, behind every line of code you write or program, you run lies the genius of CPU architecture.